Okay, guys, another type of probability problems that you'll run into with your homework are these contingency tables. So they're summarized data about certain events and factors with those events. Go ahead and read the example 3. The first thing we want to always do with a contingency table is just total up all the different event occurrences. So here I want to total up all of my early flights, on-time flights, late flights, and also total across all the LA flights and all the San Francisco flights. So I'm going to do that really quickly. Okay, so I've totaled them up and I just colored them blue so that they stand out as a total number. What's the probability that a randomly selected flight arrived early? We don't really need the probability statement, but I'm just going to do it for us so we get the practice. What's the probability that a flight arrived early? E is the letter we're denoting for the event that it arrives early. Okay, how to do this? Let's go up to our table. Here's my E column. There were 75 total early flights out of the 400. Equals 75 out of 400. It's as simple as that. Part B, what's the probability that a randomly selected flight did not arrive early? This is kind of review. We've looked at this before, but a flight that did not arrive early, we have what's called the complement of the event. With a bar above it means not E, so not early. The rule for that, 1 minus the probability of E, or just 1 minus probability of E. We calculated in part A, 1 minus 75 over 400. See what's the probability a flight originated from Los Angeles and arrived early. Okay. Again, I'm going to work on the probability statement. It'll make the calculations easier if we know what we're trying to calculate. That it originated from LA, A, and that it arrived early. A joined with E. So how we do this calculation with a contingency table is pretty simple. Okay, we're looking at the events A and E, their intersection or they're joined. Okay, so A and E are both occurring. Let's look at the event A here. Okay, and E. E is right here. Find where these two events intersect on my table. We see that the column and the row intersect at 50. There's my numerator number. 50 flights were both from LA and early out of the 400 total. Next up, let's look at the question. Suppose a flight originated in Los Angeles. What's the probability it arrived late? Okay, so we got to read this sentence carefully. Something has already occurred. So we're assuming that a flight already originated from Los Angeles. That's given information. We want to find the probability that it arrived late. So the probability that it's late given is from Los Angeles. Now, we could follow the conditional probability formula, but with these contingency tables, there's an easier way to calculate these. Focus on the given information. A is given. That is from Los Angeles. We're going to limit all of our calculations then to the given information. So I'm going to highlight it. We're going to ignore all the other numbers that aren't highlighted in yellow. Okay, now we're wanting to find the probability of L. L, just focusing on the highlighted numbers, L is right here, 75 out of 225. Again, I'm just using the numbers that are highlighted because that's given information that's already occurred. So my answer, 75 out of 225. Let's look at the next one. Are the events flight early and flight originating in San Francisco disjoint? Disjoint, recall, means that two events cannot occur at the same time. We want to justify this mathematically. So logically, these two events can happen at the same time. A flight can come from San Francisco and it can be early. So we know in our gut the answer is that they are not disjoint, but we need to justify this mathematically. Your textbook highlights this formula, but I'll also just refresh it for you. If two events are disjoint, again, that means they can't occur at the same time. Therefore, if two events cannot happen at the same time, the probability that they both happen at the same time has to be 0. So here, A and B are just general events. I'm just kind of showing a formula. This is true if A and B are disjoint. Okay, they can't happen at the same time, therefore their probability of occurring at the same time equals 0. Okay, so we're going to see if this property holds true for the events flight early and flight originating from San Francisco. Let's see if the probability that a flight is early and that it's from San Francisco equals 0. If it is, the events are disjoint. If it's not, they are not disjoint. We know from the previous example that these joint probabilities, these intersection, are where the row and the column intersect, E and F. Here's my E column and my F row. They intersect here at 25. So the probability of this occurring is actually 25 out of 400. That is not equal to 0. Therefore, they are not disjoint. Okay, last one. Are the events early and originating from San Francisco independent? Again, independent means that one event does not affect the other. So we're going to test this and we'll justify our answer mathematically. Scroll up to page 2. We have this multiplication rule for independent events. If we know that A and B are independent, one does not affect the other, therefore this statement holds. If this equality does not hold true, then the events are dependent. So let's just set up this equation here and see if it holds true in our example below. So we're looking at if the probability that a flight is early and from San Francisco, is that equal to just the multiplication of each of those probabilities? Okay, let's compute this and see if it's equal. We computed probability of E and F. The joint probability was the 25 out of the 400. Okay, probability of E is the 75 out of the 400. Total 75 flights out of 400 were early. Probability that a flight is from San Francisco is the total 175 flights were from San Francisco out of the total 400. $25 out of 400, 0.0625 does not equal this multiplied out 0.082. They are not equal, therefore E and F are dependent events.